Today we're gonna study Ampere's law. Okay, Ampere's law helps you find the magnetic field of a wire that has a current. And let's see, if we have some wire, okay, and then it has some current. This is the current I, and we want to find the magnetic field here. We want to find the B field at that point. Okay, so what we do, we apply Ampere's law. So Ampere's law says that the integral of the B field dot the distance, certain distance, is equal to mu zero, this is the permeability of free space, times I enclosed. This current here is enclosed with this Amperian loop, which I'm going to show you. Since you want to find the magnetic field at this point you draw a loop that goes like this. And this loop is called the Amperian loop. And then what you do, you integrate along the loop. You integrate along the whole loop. Now, the B field of this current here, we can know its direction at that location, at this location, here, there, anywhere on the loop. So you just use the thumb rule. You grab the current and make sure you grab the wire. Make sure the thumb follow the direction of the current. Your thumb is following the direction of the current. The current here, or the magnetic field, is coming out. So I put here a circle with the dot. The B field is coming up here. And this location is going into the page, because my fingers, they come up here and they go into the page here. So this B field, this circle here, it's like this. If I make it flat like that, so we'll be going like this. If I turn the loop, the B field will be going like this, like that. If I turn the loop. Now you can see here that this B field at this location, actually the B field here and there on the loop is the same, because actually the B field depends on the distance, how far you are from the wire. But you can see these points here, they're all the same distance from the wire. So this B field here is really constant, because it's at the same distance from the wire, same radius. So when you do the integral, this B field actually is constant. So what you integrate in is just the length, this small length, like this one here, this is dl, and you sum in these dl's, you add in these dl's. If you add all these dl's, what you get, you just get the circumference of the circle. Now, this dl here is this one here, that's dl. And the B field is here. You can see that dl and the B field are parallel to each other. Also at this location, the dl is going this way and the B field going to, so dl and B are parallel at this location. It's going like that. dl is going like this. This is dl, the B field. So at each location on the loop, the B field and the L are parallel, so the angle between them is just 0. So instead of using these vectors, we can just say the integral of B dl is mu 0 I enclosed. You see, the current that's enclosed in this loop is just this current here, so I just put I. Okay, now we got rid of the integral, we got rid of the vectors because the B field and the L are parallel. And if we use the formula, B dl is equal to the magnitude of B dl cosine the angle between B and dl. And that angle, this is just 0. So this is just going to give you 1. So B dot dl is just B dl. Now we have to go back to our original equation and then we can write B dl mu 0 I. Now, I told you that the B field is constant all over that loop, Amperian loop. So the B field can come out. And then you integrate dl. You just go along summing these dl's. And then you go all around. You get mu 0 times I. So this gives us B. When I sum all these dl's, I would just get the circumference L, which gives me mu 0 I. This equation gives me mu 0 I. Now this L here is just 2 pi r. L is 2 pi r. So now these two equations give me B 2 pi r is equal to mu 0 times I. And from here I can find the B field. Mu 0 I over 2 pi r.